So in this video, I'm going to recap the spring mass damper system components. So obviously the three components that we have to work with in these systems are spring, masses, and dampers. So let's start off first of all with the mass. So masses will typically be drawn as like a box, and they're going to have a mass, I'm going to call it M, associated with them. And what I'm going to draw on here is some applied force, which is going to be applied as a function of time, and it's going to cause our mass to move, which will also be as a function of time. So moving across to the next column, what I want to put in here is the force displacement relationship, and we're going to do it in both the time domain and the frequency domain. So we know that the force is equal to mass times acceleration, so we can write this as F is equal to the mass m multiplied by the acceleration of the block. So if x here is the displacement, we know that acceleration is the second derivative of displacement. So it's going to be the second derivative, which we can write as x double dot. Now what we want to do is move this into the frequency domain. And to do that, we need to take the Laplace transform. So we know that f here is a function of time. So it's going to have a Laplace transform, and I'll put it in uppercase F. M is a constant, so it stays out the front, and we know that x double dot is a function of time. So this is going to become, when we transform it, s squared x. Okay, and what I've done here is, when we've Laplace transformed it, I've gone from the lowercase in the time domain to the uppercase in the frequency domain. So that happened for the force and also for the displacement. Alright, so let's move on to the next component, which is a damper. So this will be typically drawn, I'll draw this one against a wall, but like this. Again, let's give it a force, which will be as a function of time, and we'll look at its displacement as well as a function of time, x. So we need to give it some kind of constant, the size of the damper or its damping effect, and I'm going to call it c. So now we need to go and look at the forced displacement relationship. So in this case, the force acting through this damper is going to be proportional to the velocity of the damper. So we know that the constant associated with it is c, and velocity is the first derivative of displacement, so we're calling displacement x, so it's going to be x dot. So now again we want to convert this into the frequency domain, which means we need to take the Laplace transform. So we know that f here is a function of time, so when we take the Laplace transform of it, it's going to go straight to uppercase F. C is a constant, not a function of time, so it's just going to stay out the front. And we know that x dot is going to go to sx, okay? One dot means it gets one s out here. Alright, so we have one component left, and that's the spring. So I'm going to draw it up against a wall again, and that's what you'll typically see springs drawn. Again, let's apply a force to it and measure how far it moves. And we're going to give it a spring constant, which I'm going to call k. So again, we want the force displacement relationship, and starting in the time domain. So we know that springs have a linear relationship between the force and the displacement, and so we can write that as F equals kx. Okay, so however far this spring moves off the wall, that's going to be proportional directly to how much force is generated. So again, now we just need to put this into the frequency domain, and this one's fairly straightforward. F again is a function of time, so when we Laplace it, it's just going to go to capital F. K is a constant, it's not a function of time, so it's just going to stay out the front. And x is a function of time, so it's going to get transformed, but since it has no dots on it, no derivatives of time, it's just going to go straight to the uppercase version of itself. So that's, the force in the frequency domain. So with all these spring mass damper systems, the equation that you need to solve when you go through your free body diagrams is that the sum of the forces have to be equal to the mass times the acceleration. You can alternatively write it like this, which is exactly the same thing, just with the double dots on the top of the X. Okay, so that's pretty much all there is to the spring mass damper system components, and I'll run through an example or two after this.